Hey guys, Kevin here. I wanted to make a quick correction or response video to Network Chuck's recent uh, marketing, Cisco-sponsored marketing video on Wi-Fi 6. Um, to start it off, just to say I've never seen Network Chuck before or any videos from him. He has a pretty well put together video. The problem is that one, it's mostly marketing focused, so the engineer types obviously always are conflicted with those marketing videos, slideware, etc., the hype that they try to generate. Um, but more importantly, there's some technical uh, facts that are incorrect with his video, which is challenging because there's a lot of people viewing the videos, and that information that is not correct is spread amongst those people that watch it, and network engineers like me have to correct folks all the time when they learn these things that aren't true. So we're going to go ahead and kick off this video. I will say, since I'm from the South here, that bless Chuck's heart um, before we get started here. So let's watch this video. It looks like his link
Supported 5 gigahertz channels.
His link goes right into the middle, so let's start it over here.
I'm in a mall right now, and I'm trying to update my Instagram story. And I'm connected to the public Wi-Fi. You probably guessed it's not working, and you probably already know why. Because I'm connected to public Wi-Fi. Let's see. No, still nothing. What should I do? Well, it's what most people do. We disconnect our Wi-Fi and we connect to 4G, and it works 10 times better. Why is it that 4G cellular technology is so much better in public places and in a lot of places, even at work or school, than your good old standard Wi-Fi? It feels like cellular technology has gone so far, where Wi-Fi is kind of still in the Stone Ages. Well, I got good news for you. That's about to change. Wi-Fi 6, 802.11ax.
Now, first off, I would say that in this video he talks about how 802.11ax is about efficiency, or Wi-Fi 6 is about efficiency, and that is true. It's current Wi-Fi is pretty inefficient, and it doesn't use the spectrum real well. The challenge is that he goes to a mall to talk about public Wi-Fi being a problem, uh, and tries to show that it's a high density fix, but in this mall there's not any people, right? It's not a density issue. It's probably a bad circuit, or um, just bad Wi-Fi in general. So like when you look, I pulled up some pictures here. This is an actual high density problem that Wi-Fi 6 will address, right? Efficiently communicating to all these clients. In his picture, it doesn't show that. Props for going to the mall and getting a video. It gives you the illusion that AX is going to fix public Wi-Fi. Well, public Wi-Fi in that scenario here, where there's nobody there, is just bad Wi-Fi. When you're trying to do high density at a stadium or a packed um, mall, that's where AX is hopefully going to shine through. But your example, you start the video off, unfortunately, with a bad example, just kind of trashing public Wi-Fi. That said, recently we just had the Super Bowl, and they passed 24 terabytes. So the current Wi-Fi is good enough to pass a lot of traffic if designed properly. So AX is going to be an improvement in efficiency, absolutely, and it will help in high density areas, but in your video here, it's probably just bad Wi-Fi or a slow circuit.
So let's not do that Wi-Fi alliance. So how will Wi-Fi 6 solve our high-density, congested areas when we're in schools, malls, airports? How will it solve those problems? Well, before I jump into that, and
Yeah, high density. Your video of the mall was not high density.
it's a whole slew of amazing things it does. Before I jump, all right, light bulb. Here's your color change. We're done here? Okay. Computer, here's your YouTube video. Alright, we done here? Okay, we're good. Again, this is one at a time. This is how it currently works from 802.11 AC and before, everything before. This is how our wireless works. Now it gets even worse. So not only is he...
It's not actually true. We had multi-user MIMO was introduced in 802.11 AC. And also this stuff happens so fast that queuing up information to these devices, unless it's congested, there's plenty of time. This is why Wi-Fi works fine in most scenarios, except for it becomes exposed in ultra high density environments.
only able to talk to one. So the AC in previous standards had something called OFDM, or, now here we go, this is the big one, orthogonal frequency division multiplexing, which basically took our highway, our big channel, 20 megahertz, 40, 60, and we added lanes to our highway.
There's no 60 megahertz channels. 80 is what you meant to say.
So we kind of put our...
Though there's 160. I don't know anybody that actually uses it though.
channel into what's called, or we cut up our channel into what's called subchannels. And the purpose behind that is just like any other highway. You think we put a lane in there so we can avoid interference.
It's not really subchannels, it's subcarriers.
Interference with the other cars going across the channel. Stay in your own lane. That's basically what this is for. That's OFDM. Okay, cool. We divided up our channel into subchannels. Awesome. But you still have to give all of those subchannels, all those lanes, to each device one at a time. We still have that same inefficiency. Ah! So even though my phone, refreshing its Twitter feed, only needs like half a lane of traffic, he gets the whole highway just for him, just from...
So I would note here is that bigger stuff is going to use the channel for longer. So the small updates, they do use the whole channel, but they use it for less transmit opportunities.
That's smart. Not really. No, it's stupid. Now again, I want to hit this point home. You're not going to have a lot of issues with just 3 devices in your network, because boom, 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 it's really fast. But when you're on a public Wi-Fi, you're at a conference, and you're sharing that one access point, that one channel, with maybe 20, 30, 40 devices, well then, that's a lot of devices talking to one device at a time, which is why you...
And I would note with a 20 megahertz wide channel that you have an example, 802.11ax is only, it only has 9 resource units, so it can't talk to 40 devices at the same time. Just note that. It makes it sound like, oh, you know, AX, you can talk to 40 devices at one time. It's not the case.
Feel the pain, you start to feel the hurt, the congestion, all the contention. It's ridiculous. It's like 40 people all trying to talk to one guy at a time, and he's trying to talk about. It's like we've gone from a hub to a switch.
Now, a lot of the engineers in the Wi-Fi industry really get upset with this. And when AC came out with multi-user MIMO, they said the same thing. It's going to make it switch-like. And what's important to note here is that a switch is full duplex, and you kind of expect that you're going to get full capacity out of all the ports. With OFDM MA, you're able to divide up a 20 megahertz channel into 2 megahertz, down to 2 megahertz subchannels. But it's not full duplex. So in this example, if you want to call it a switch, you really need to call it a half duplex switch with shared bandwidth, right? Because you're not going to get the full 20 megahertz channel to 40 devices at the same time. It's not technically like a switch. And it upsets a lot of people, engineers that have to explain to people, hey, this isn't really like a switch, because they don't understand it. And the marketing thing kind of rubs a lot of engineers the wrong way. I personally don't care. So
it's huge. It's crazy. So with Wi-Fi 6, we take that OFDM, the orthogonal frequency division multiplexing, and we add one more letter to it to make it amazing. We add an A. So now it's orthogonal frequency division multiple access.
Yeah, the M changes from multiplexing to multiple just FYI. It's not just the A. We didn't just add the A.
Let me add that A there. Now, what's so special about this? Well, the headline, I'll go ahead and ruin it for you, is that the AP can now talk to several devices at once, whereas before you could only talk to one device at once. Okay.
Again, we've already had multi-user MIMO in the past, and we still have it with AX. You're actually going to get multiple user OFDM multiple access as well. So if you look here, let me pull up this slide. Where's it at? I got slides somewhere here. Here we go. So you have multiple user OFDMA. And what you can see here in this example is that this is transmit opportunities, right? So you see your different transmit opportunities here. Everybody has to wait, right? You can't receive while this is being sent out. You see how that's got the wider channels, but then it also has how many streams, data streams, can be used. So these are 4 different clients getting transmitted to at the same time. Now when you add the OFDMA on top of the multiple user MIMO, it gets really complicated, because not only can you have the 4 streams, actually up to 8 in AX, you can also do multiple access as well. So you could start to transmit to a whole bunch of different things at the same time. And some of these, when you start to combine the signal, right, this is how you get your bigger data rates. So this is 2 streams of data shown here or here as well. So higher bandwidth stuff like trying to download a video versus your smartphones here, which you could have done in the past. You don't see it, the adoption rate on multiple user MIMO being that great, but it's available, it's been available, and it's continued into AX.
Big improvement. But it takes it even further. And reserved pieces. These are also referred to as resource units, or RUs. So for a Twitter feed, we might just need a little bit of space right here. And that's how much we're reserving in that channel for the Twitter feed. And then maybe the light bulb only needs just a little chunk right here too. Just a and then the laptop, he's streaming video, so he might be streaming a huge 4K video. So we'll give him some more stuff. We'll give him maybe 3 whole sub channels, and that was actually 2.
So what you've done here is you're showing one transmit opportunity, but you're showing 2 things in the same lane, right? And that's not how it works, right? You can't talk to the 2 devices at the same time, or in the same transmit opportunity, 2 different devices. So this one here should be down here, right? This is not how it works. So this is, say, 2 megahertz wide, and this is 4 megahertz wide. Your other 2 megahertz needs to be down here, and it's all in one transmit opportunity. So going back to the slide, notice here's transmit opportunity 1, 2, 3, 4, 1, 2, 3. But what you notice is you don't see 2 different things in the same transmit opportunity, because it just doesn't work that way.
I can count, don't worry. So no longer is the access point in a big battle with all the devices on his network. No, he's in control now. He can say, everyone be quiet. Okay, phone, you can send data. I'm sending stuff to you. We have this much of the channel allocated. And it's beautiful. Versus what we had before, this is groundbreaking. Can you imagine what it's going to do for the services and devices that require like a really great quality of experience or quality of service? Like, let's say, for example, my phone was about to place a VoIP call.
So this isn't true. You still have to contend for the airtime. And in the past, we've been able to request to send and clear to send. It's not. Oh, you should. Let me find this here. You can reserve the airtime. Other devices, Wi-Fi is very friendly, so it listens. It listens before it talks, and you have a protocol where you send a request, and then you get a clear to send it. Right now with AX, you can request smaller smaller channels, right? Or reserve a smaller channel instead of the whole 20. And you can do that for a bunch of different RUs on that 20 megahertz channel. So you could talk to multiple devices. So I don't quite understand what you're trying to refer to here, but request to send, clear to send has been around for a long time, and you still have to share the air. You could start to get into the coloring that you talk about later, where you can ignore stuff that's not in the same color group as you, but then you run the risk of collisions and frame issues. So it's not like you get QoS with this 802.11ax. It doesn't prove it, but it's not QoS.
Right? And it's over with thousands of little devices that communicate.
So again, the AX and efficiencies are really when it's a high density, a lot of congestion, a lot of things are trying to send a lot of data, like a stadium where everybody's uploading videos and pictures. The IoT is probably going to be more focused on the targeted wait timing that you talk about later, not necessarily sharing channels, if you will. Most of these manufacturing things that you're talking about, they don't really have a lot of channel use or high duty cycle because they're not sending a lot of data. They just need a little small slice. But being able to have the IoT devices sleep for a long time instead of always being connected and sending useless traffic is the benefit. So at this point here, I don't see IoT being that much better because we have AX, other than the targeted wait timing.
With your access point IoT, it's huge for conferences where you have a ton of people connecting to.
Here we go again with the multiple devices in the same lane. That just isn't how it works. The targeted await time, there's a good Ruckus blog post about it as well. That's really where the IoT, they could sleep for a long time and not waste that battery life and only transmit when it's actually needed. So just a bad example, I think.
One AP, like Cisco Live. And yeah, AX is faster. The I think 802.11ac was around 866 megabits per second of maximum throughput when you're talking like one device.
That's not even correct.
Like one AP to one phone using one antenna. And with AX,
so let's see, MCS rate, WLAN pros. Keith, let's see if this is. Yeah, this is the best one here that kind of shows you everything. And what you can see, this is AC. So depending on, this is based into how many streams. All APs are required to support 2 streams. Devices can only support 1 stream. But if you look, this goes up to 3 streams. You can see the different data rates. 20 megahertz wide, 80 megahertz, 160. But yeah, so the max is a lot higher than, I forget what you said, 866, is that what you said? That's really going to be a single stream at 80 wide, or 2 streams at 80 wide with a short guard interval. Single AP, single stream at 80 is 433.
It goes up to like I think 1200 megabits per second. So it is faster. But that's just.
So if you look, when you go to AX, they add a couple MCS rates, 10 and 11, that you don't see here because this is AC. And it also goes up to 8 streams, right? So when you start to add 8 streams, that's where you get those big numbers. But what we've seen is that most devices are playing the 2 stream area, right? Even MacBooks, I don't think. They might go up to 3 streams, but it's one of the few devices that actually could hit those big numbers. And again, to get those big numbers, you really have to run super wide channels that nobody does, right? Because it ruins your channel reuse.
An afterthought when you look at OFDMA, it's so much better. The 2.4 gigahertz spectrum. It's back! He's back again. All right. Why is that cool? Well, AC, the last standard we just released, it's been a while, it only supported 5 gigahertz channel.
So when we went from N to AC, the real improvements, we did get a couple more modulation or MCS rates added, but the real benefit for those big speeds was the wider channel. And since you only have three non-overlapping 20 megahertz wide channels, there wasn't really a good reason to update it. So staying N for your 2.4 and not going to the AC wider channels, wasn't really a big deal, right? There wasn't a reason to do it, or they would have done it.
Do that. They will, if they hear any kind of other channel, other wireless SSIDs, networks out there talking, even if they're far away, if they can just hear the muffled noise.
So since this is a Cisco video, just to be clear, there's some knobs that you can turn to change the threshold where you don't play nice, right? Where you can ignore weak signals. Not that the coloring isn't going to be an advantage. Um, Cisco does have knobs where you can ignore stuff in a noisy environment.
They'll stop and listen thinking it might be for them. This is called CCI, or common channel interference, and it's dumb
It's not common, it's actually co-channel interference.
because it interferes with our wireless performance. Even if you only have a small number of devices that support AX on your network, it will instantly improve your wireless, just like that.
I think they said that you need around 30% AX before you start to see any advantage.
I'll catch you guys later. I'm gonna brew some more coffee, actually.
So, this video is very well put together. Unfortunately, some of the technical details were just not correct. And I didn't mean to slam Chuck here in this video, but it's dangerous. Like if you look, we got almost 27,000 views, and people take this information as the gospel. If you look at the comments that he has, everybody, except for my comment here, about 70%. But if you look through the comments, everybody, oh, this is so great, and this is, all correct, and it's challenging because people are going to take this misinformation and run with it, and guys like me are going to have to have hard conversations with customers to correct them. So that said, I'm going to end the video. Sorry, I wasn't trying to bash it, Chuck.